Okay, friends, welcome back. We're going to take a look at the first derivative test. So you know what intervals of increase and decrease are, and we're just going to sort of take it to the next level where we can kind of figure out intervals of increase and decrease on functions that we don't know what they look like, okay? Or functions that we do but are more complicated. So let's get into it. Oh, new term, critical number. I want you to be clear of what a critical number is, and I want you to be able to find absolute minimum or maximums for graphs such as this. And here we go. So first things, let's do a little review here. How do you graph that one? So let's make sure you know how to do that. Okay, first things first, we know because we know what a polynomial function looks like, that it has a y-intercept at 1, it is a function of degree 3, so it probably looks something like that, or maybe it looks something like that, and we know that because it's positive and it looks something like that, okay? So we're expecting two places of increase. We're expecting increase sort of on that interval, and negative or decreasing on that interval. So in order to find those, we need to find the critical numbers. And a critical number, it can be found when the slope is 0. And there's another stipulation which we'll add later. And here we go. So what we're going to do is we're going to take the first derivative and we're going to factor it. Then we're going to set it equal to 0. Because remember, what we're trying to do is find the points at which the slope... Yep, have a good one. That was a great Rob Kinnear going by. Okay, so we know that the slope is 0 in those spots. And so we're going to set it equal to 0, and we're going to find our critical numbers. Here's 1 at -3, and here's 1 at -1. Now, this is consistent with our drawing, which tells me that I need to shift that over a little bit so it looks more like that. But we're going to be looking at graphs today where we don't know what it looks like. So let's pretend we don't know what the graph... Well, let's approximate it with what we know. Okay, so we know we have a y-intercept at 0, 1. We know we have critical numbers here, and so we know somewhere along the way here we have critical numbers, meaning that the slope is 0 somewhere along there. Okay, then what we have is, we know its general shape, so we know it has to look something like that. And work your hand-eye. I'm using a mouse, make sure it goes through that y-intercept. And of course, that's what it looks like. And so when asked to find when is it intervals of increase, well, it's clearly increasing before -3. And after 1, and it's decreasing in between those. So that's what I've stated there. Now what I want to do is help you see, how would we do this if we didn't know that it was a polynomial function? And you're going to look at those today. So we're going to take a look at this thing. So remember what we did is we created, what I'm going to do here is I'm going to get the same information by using an interval table. Here's what it looks like. First off, I'm going to take the derivative. I'm going to factor it. So here's my derivative. Then what I'm going to do is I'm going to set my intervals. Remember my intervals being that where we got 1 at -3, because that's a critical number, and this is a critical number at -1. Okay, those are my critical numbers. So notice x is less than -3, it's in between -3 and -1, and it's larger than -1. Then what I'm going to do is I'm going to test any value to the left of -3. It doesn't matter which value we choose, because remember in this graph, all these slopes here are positive. So it wouldn't matter which one I choose. If this is positive, then they're all positive. Or if one's negative, they're all negative. Okay, so let's get back into this guy here. Actually, I'm going to just clear the screen there. Hopefully this will work. Beauty. So we're going to clear the screen here. Here's my interval. I'm going to choose a number less than -3, like -10 or -5 or -100. If I put -5 in here, will this be positive or negative? It's going to be negative. What will this be? This will be negative. So we're going to have a negative and a negative. And a negative times a negative is a positive, which means it's increasing. Okay? There we go. We're going to do the same thing in this interval. I'm going to try -2. If I put -2 in there, that's going to be a positive value. That's going to be a negative. Negative times positive is a negative, and it is decreasing. Okay, so we got that. And I'll do the same thing in the bottom, and you can do that on your own. And it's increasing. So basically I have this interval where it's increasing, it's decreasing, it's increasing. So I can approximate the graph. I know the graph looks this form. It increases, decreases, increases. So even though we didn't know it was a polynomial function, that graph is telling me that that's basically what's happening. Okay, so this is all sort of warm-up stuff. So please pause the video and go as far as you can without listening to my voice. Okay. Okay, so I trust that you're listening to my voice now because you had trouble with this for some reason. Given the table above, listing intervals of increase and decrease, sketch a possible graph. Okay, perfect. Well, I can just see that it's basically that situation there, isn't it? We wouldn't necessarily know where it was. All of these are acceptable answers because we don't know where the relative mins and maxes are. Okay, and that's what we'd have to find. Okay, and so now we're going to shift gears and I'm priming you for new stuff. So I just need to make sure that you are clear on a few things like restrictions. Does this function here have any restrictions? Please pause the video again and see if you can figure out where you need me and where you can do this on your own. Okay, this is a polynomial function with no restrictions. This is not a polynomial function. And notice here, algebraically, we know that x can never be 0. So we certainly have a restriction at x equals. Okay, so this is not a polynomial function. And you can see this gap here. And we know that x cannot equal 0. So this does have a restriction at x equals 0. This one right here, any restrictions? Of course, x cannot be 20, and that it's also consistent with this graph. There would be a spot right along there where x never actually gets to 20 and the function goes up. Okay, x equals 20. Let's look at this one. Does this one have any restrictions? Yes, it does. Once again, x can't be -2, and that's exactly what we see here. There's -2 and so on. Okay, let's define critical number. Again, you know that there's a critical number right here and right there, whatever those x values are, that's the critical numbers. There's another time a critical number happens, and that happens when the slope is undefined. That happens in instances where the slope, where the curve is approaching infinity or negative infinity. So let's make sure you've got that. Okay. All right. How many critical numbers does this one have? You're going to say 2. One right there, one right there. The slope is 0. Let's look at this guy. How many times? This one has no slope of 0. That's almost 0, but not quite, so we're not going to count this. This one has one critical number, and it happens right in there. And we can see it, one critical number. How many critical numbers does this one have? Once again, there's no slopes of 0, but at this point right here, there's an asymptote here. We know there's going to be a critical number right there, negative at 20. Okay? Now, one critical number. Let's look at this one. How many critical numbers does this have? You can see that this one has critical numbers right here and right here. And hopefully you don't miss this one where the slope is 0. I want to show you what that graph looks like. And we'll spend a little bit more time there just making sure you see that. So you can, of course, access this on the slide deck yourself. But I'm going to just play with it right here. Okay, so we have there's one region here and the slope here is positive. On the other side here, the slope is also positive, but that's in between this critical number and this critical number. On the other side of that, it's negative slope. So it's a positive slope, negative slope, and then one more time, positive slope. So please note that you could have a slope on, actually, let me just show you the interval on this guy here just for a second. Okay, we can see that it is increasing on this interval, increasing on this interval, decreasing and decreasing. You will get to the point where you should be able to look at that and know whether there's a relative min or a relative max. And I hope you can see that there's definitely a relative maximum right here, but obviously if it's increasing on one side and increasing on the other, that's not a relative min or a max. It's either going to be sort of something that the graph looks like this, so it's sort of like a cubic kind of thing, where it's increasing, but there's a point of inflection right there, or in this instance what we have is a asymptote or a critical number where the slope is undefined. Alrighty, so now what we need to do is kind of get started on this. I need to clear the screen here. Gosh, the screen is not clearing. It looks like we're going to have that mess for a while here, okay? So, we have to walk through all that stuff there. Jeez. Oh, we already did that, didn't we? Yes, we did. No, we didn't. Okay, step 1 in this problem. Excuse me, here we go. So what I want you to do is find any relative maxes or mins. Okay, so what we're going to do is, again, start off with an approximation. I know it has a y-intercept at 1. It's a positive quartic function, so it's going to be a W kind of shape. And just the question is, where does it go through that y-intercept? So that's what we got to find. Okay, So what I'm going to do is I'm going to take the derivative here, which I've done. I'm going to factor, which I've done. I'm going to set up my intervals less than -1, in between -1 and 0, in between 0 and 4, and greater than 4. I'm going to test values that are less than -1, like maybe -10. And if I do that, that would make this negative, negative, and negative. Overall, it would be negative. That's why this is decreasing. I choose a number between -1 and 0, like maybe -0.5, which would make this one negative, this one positive, and this one negative, which would make it positive. That's why it's increasing. So as we walk through this, you're going to see what's happening there. And so we know, so we have a decrease, increase, decrease, increase, that we know that the graph sort of looks like that, and you know that's consistent with what we knew anyway, okay? So keep that knowledge in the back of your mind. Okay, now what we're going to do is we're going to look at a more complicated. Oh, and let's just talk about this. So we knew that this guy here was a relative minimum. This was a relative maximum. That was a relative minimum, and we knew that. The way we knew that is by simply finding the y coordinate in time. Yeah, we'll leave it at that. Okay. So this one is more complicated, as we will see. So what we're going to do is we don't know what that function looks like. So determine any local minimum maximums of the function. Okay, so what I'm going to do, same old thing, is I'm going to take the derivative. First off, I'm going to write this in exponential form. I'm going to take the derivative, which I've done right here. Okay, I'm going to set it equal to 0, because remember, we're looking for the spots where the slope is equal to 0, and that's what I'm doing here. So the critical numbers are at 0. Also, please note, right here, there's a restriction at x equals 0. That's going to be a critical number, because the derivative is also going to have that same issue. Okay, so we know that there's going to be a critical number at 0, and we're going to try to find the other ones. Okay, so at this stage here, we are going to set this equal to 0. Okay, and so which is what I've done right here. I've set this, I haven't set it equal to 0. You don't have to do this, but I wanted to make a common denominator here. You can decide. Other people would have done this. They would have just said 0 equals 1 minus 1 over x squared and left that as our derivative, and then gone 1 over x squared equals 1. We're going to cross multiply, so 1 equals x squared, and then x must equal plus or minus 0. Or plus or minus 1. Notice that I can do the same thing here. I can see that x cannot be 0, one critical number. X equals 1, critical number 2, and x equals -1, critical number 3. Okay. Alrighty. So then we're going to get down to here, and we've got our critical numbers. Then what we're going to do is we're going to test values on the intervals. Less than -1, in between -1 and 0, da, da, da. The reason I like this format here is it makes it easy to test the intervals, because when I put -10 in here, I'm basically going to have a negative times a negative over a positive, which is positive, increasing. And then I put a -0.5 in here. It's going to be negative times a positive over a positive. That's negative, so it's decreasing, okay? Which gives me a sense of what this graph looks like, and we can fill all that out and decide it's increasing, it's decreasing, it's decreasing, it's increasing. So that sure looks like a relative max and a relative minimum, okay? Other than that, we don't have the experience to know what it looks like. On Desmos, let's take a look. That's what the graph looks like. It was increasing, decreasing, decreasing, increasing. And there's our relative minimum, relative maximum. So when we look at the graph, that's what it is, okay? So we can clear that up and find our local minimums or maximums and go from there. This last one, it's kind of more of the same. It's just a bit more complicated. So we'll take a look at this together. So pause the video and give it a go. Okay, welcome back. First thing we know is there's going to be a restriction. X cannot equal 0. So right off the bat, I know one of the critical numbers is 0. Okay, then what I'm going to do is turn this into exponential form. Which I've done right there. Then I'm going to take the derivative. Okay, then I am going to, ew, this looks really yucky. I like to switch it back to, what do you call it, square root form, but some of you will just set this equal to 0 and rearrange it and go for it. But I know right now that the first derivative is undefined when x equals 0. We already knew that because there was a restriction. At this level here, what I did is I converted this. So notice that the negative exponent puts those things in the denominator, and the 2 is obviously in the denominator because that's where it is originally. I created a common denominator. You don't need that. You could set it equal to 0 now and put the 1/2 on the other side or not. Okay, so I set this equal to 0. I'm going to cross multiply here, and that times that is going to be 0, leaving me with this. Then I'm going to take the 1 to the other side, and I'm going to take the cube root, so x equals 1. Okay, and that lets me know it was just asking critical numbers. So there's going to be a critical number at 1 and a critical number at 0. Okay, so that's what the graph looks like. If you wanted to see a better example of the graph, that's what it looks like. Okay, so obviously very tricky. Please self-assess. Please take a look at here you could certainly add evidence that you're learning the vocabulary, that you know the vocabulary, and to reflect on your thinking and how you're making decisions. So please fill in your digital portfolio as you can, and we're going to call it there. Good luck.